Hi, welcome to Train Signal. This is the lesson, New Features of DHCP. So as we get rolling into our formal content, I want to draw your attention to DHCP as our first major topic area. DHCP's new features is going to be our first area of discussion. Certainly DHCP is not a new feature of Windows Server 2012 by any stretch. It's been around since early days of Windows NT. Its intent is to help solve the problems posed by manual IP address assignment. Consider the challenge of visiting dozens, hundreds, thousands of even computers, manually configuring IP addresses for each. If everything goes perfectly, it's a lot of tedious grunt work. You've got a clipboard with a list of IP addresses. You visit each computer, configure the IP address manually, hoping that you don't mistype anything, check the IP address off your checklist, and then move on to the next computer, hoping that you don't inadvertently configure the same IP address onto multiple computers or misconfigure one. That's a recipe for an IP address conflict and lots of wasted time. So what's our solution? DHCP, an automated IP address solution. So we're going to focus on that here. We are going to talk about some of the new features. The mainline functionality we're not going to discuss in detail. I will do a quick terms review and take you on a quick guided tour through the DHCP interface just to make sure we're speaking the same language about DHCP's basic functionality. But we're going to move quickly into new features of redundancy, failover, a number of ways to be able to make DHCP more robust and reliable so that it'll serve your organization more effectively. So to get started, I want to kind of set the stage here with a kind of a terminology review. We're going to talk about the new exciting features of Server 2012's implementation of DHCP. We're going to explore the new features for redundancy and things of that sort. But with that idea in mind, we're not going to cover every detail of what's ordinary mainline functionality of DHCP. But to make sure we have all of our terms straight, I'm going to do a quick review of high-level DHCP functionality. So we're going to do a quick discussion of scope creation, what to do with the IP addresses that are in a scope, how long they're made available to clients that acquire them, that sort of thing. So with that idea in mind, I'm going to jump over to our demonstration system where you'll get a chance to see this live. So now you can see I'm on New York City Server 1. Server 1 is going to be a good friend by the time we're done with this class. We're going to spend a lot of time on Server 1. Server 1 is a Windows Server 2012 Standard Edition server, and I'm going to use it to be able to illustrate just some DHCP basic functionality here. To launch that, of course, I need to get into the console. Most everything that I need to do in Server 2012 is accessible from Server Manager. DHCP is no exception there. Tools menu, there's my DHCP console, within which we've got this interface. We've got support here to be able to explore the basic functionality of DHCP as it relates to our particular New York City Server 1 server, inside of which two high-level containers for IP4 and IP6 IP address management. Server 2012, of course, supports both IP4 and IP6 IP addresses fantastically. It's designed with that idea in mind. IP version 6 in general, less of a concern for us as far as needing IP6 based IP address support. However, it is part of DHCP's capability, so we will explore it there. We're going to focus first on IP version 4, which is of course going to be our main focus, within which I want to be able to add a scope. Scope is a container of IP addresses I can deploy to multiple clients, inside of which I need to identify its name. Each scope gets a name, and this is going to be one of Global-Mantix's New York offices. So let me create a scope for that. So this is the NYC office scope. And that's going to need a range of IP addresses. I'm just going to use the 172.18.38 range of addresses. So I'm going to say that, for example, we're going to let this be a fairly small office. It's going to use IP addresses from .50 up through and including 172.18.38.75. So 25 computers, 26 computers. I'm going to use a Class C style subnet mask. Again, now why would you want to do these sorts of things? That's something that we're going to develop in more detail in the installing Windows Server 2012 class. So if you haven't taken that one yet, that might be a good use of your time if you haven't done so already. But that being said, by way of moving forward, So, exclusions and delay, I want to make sure that we're able to lock away certain IP addresses that we don't want to deploy. Maybe they're going to be servers in my environment. I don't want them to be handed out automatically. I'm going to configure them manually. But nonetheless, I do want the DHCP server to be aware that they are part of that range. This is a way to do so. Subnet delay in the bottom right corner is one we're going to focus on a little bit later as we look at some of our failover protection as it relates to DHCP. But for the time being, I'm going to make no changes in this particular box. Lease duration, IP addresses are assigned for a particular lease period. Clients who request an IP address go through the DORA, discover, offer, request, acknowledgement phases. As the client requests an IP address from a server, the server responds with an offer. The client accepts the offer and requests that it be leased the use of that IP address. The server responds with an acknowledgement saying, yes, you've been given the lease for a certain period of time. Much in the same way that if you rent an apartment, you sign a lease and you get to use the apartment for a certain period of time. If you don't renew your lease by the end of that lease period, you're required to give up that resource. Same thing here. Clients will request an IP address for a certain period of time. Here, 8 days is the default, and that'll be fine for our purposes. We can go further on to configure options, but I'm going to approach this from a slightly different angle. So I'm going to bail out of the wizard here and say, no, I'm not going to configure options just at this point. We have created a scope. Scope is a container for IP addresses. We can see that the address pool, the range of available addresses, includes the set of addresses that we identified that we would include. So far we're in good shape there. We've got a range of addresses to be able to deploy. Within our scope, there's a number of important items that I want to draw your attention to. There is room here to identify the list of address leases, places where a client computer has retrieved an IP address, and we'll be able to see that in the list here. Reservations are places where a client can be assigned a specific IP address that's handed out by DHCP, but where a given client will always get the same IP address from DHCP. Maybe the CEO of the company wants to have a particular IP address. So let me create a new reservation for the CEO. And we're going to assign to the CEO the .50 address. So how does the DHCP server know when the CEO's laptop connects in? We're going to supply a MAC address, the 48-bit code that identifies that particular user, user's network adapter card, the particular NIC on that user's computer. So by way of example, 48 bits worth of hex code, 1, 2, 3, 4, 5, 6, 7, 8, A, B, C, D, for example. We're using hexadecimal. Hexadecimal numbers range from 0 on the low end up to as high as F. Everything A through F representing numbers 11 through 10 through 15 respectively. And there we go. So we've got a reservation set up for the CEO's laptop. He's got the .50 IP address. Below that is the section on options, and here we really get into some detail that's going to be important to our later discussions. Scope options allow us to supply additional pieces of configuration about the network. Important things like which default gateway should I use to be able to gain access to the network. We can define in here which DNS server to use to be able to go retrieve IP addresses for a given known computer name, things of that sort. So those things are vitally important to us. We're going to be able to configure them through this bit of interface. So I can configure quite some healthy long number of options, and there's a particular one that's going to be of special interest to us in our later section on option 81. An important item that appears on the exam requirements for this particular set of material, for those of you that are heading towards Microsoft certification, is that it does address the issue of super scopes and multicast scopes. Personally, I've rarely seen them deployed in production environments, but hey, it's worth covering, if only because it is a potential test question item. So if I go right to IP version 4 and right-click, I have an option I didn't see a moment ago to create a new super scope. Super scopes assemble multiple scopes together into a larger collection. I've only got one at the moment, but I could theoretically assemble multiple scopes together into my new super scope. And I could assemble what might well be multiple scopes together into a larger collection. The reason we might use this is in a case where we've got a large office that's rapidly undergone some expansion. We've got a lot of new people that just moved into the office. This office now has many more people in it than we used to. We used to fit everybody we had on one scope. We find that we just don't have enough room for everybody anymore. We need another scope to be able to absorb that need for more IP addresses. Well, the challenge is, I can't go larger than the number of IP addresses in my scope. but I got more people in that same network who need IP addresses. One solution might be to assemble multiple scopes together into a super scope. When a client retrieves an address, they get it from the range of possible IP address ranges that are part of the super scope assigned on that computer. The challenge there is I do need to configure the routers to be able to recognize these IP addresses, despite being part of different IP subnets, are nonetheless part of the same logical network within that organization. So there's router configuration details there that you'll want to explore if you're setting up superscopes. But long story short, a superscope is just a collection of scopes that hang together as a group. In this case, I've just got one in there. Real world, it could be some much larger number of scopes. Another kind of scope that's worth discussing here, the multicast scope. Multicasting is a neat technique to be able to deploy content into a network in such a way that multiple computers all listen to it at the same time. Most of our IP communication is what we'll describe as being unicast communication. I send a message from one computer, it goes directly to some one other computer, and that's it, and that's where it stops. Multicast scopes are used in a case where I want to send information out that multiple computers will receive at the same time. A common use of that, imaging technologies. If you're deploying Windows 8 clients into your new network, you might have an imaging scenario in which you've got a Windows Deployment Services server that's going to deploy a Windows 8 image into your network, and multiple computers in your network are going to be simultaneously listening for that transmission. That's different from the traditional unicast communication where the server sends a complete set of the image to one computer and another complete set of that same image to another computer and another complete set of that image to yet another computer. By sending it just once and having everybody listen, we reduce dramatically the amount of bandwidth that's consumed on the network. So multicast scopes are nifty for that. Let me create a multicast scope. So, IP address ranges. One important thing about multicast scopes is that there is a dedicated range of IP addresses that can be used for that purpose. And you can see them here. The 224 through 239 networks are the only ones set aside by the people who manage the IP address space. The Internet Assigned Numbers Authority have made available for multicasting. So you got to make sure you've got an appropriate multicast scope license to you. So anyway, let me take that 224 network. Let me assign IP addresses 224.0.0. We'll just use a fairly small range. 224.0.0.10 through 224.0.0.30. Again, we can set an exclusion range if we choose to. And we assign IP addresses to a computer for a certain dedicated period of time. Default multicast IP address duration there we can see is 30 days. Do I want to activate it? I'm going to say no because I'm not really intending to demonstrate that fully here, but I just want to illustrate that we can create them. And in general, in a way that's entirely analogous to what we've seen with our unicast style scopes. So our next important topic is what's referred to as option 81. Sounds fancy. It's not quite as sophisticated as you might imagine, but it is an important configuration, and it'll become very important as we head into our later sections on the IP address management module that's available for Windows Server 2012. Very exciting piece of functionality. This is going to help kind of lay the groundwork for what we're going to do in that later section. What's important to recognize first and foremost is that there's an important relationship between DHCP, who we've been discussing, and its partner in crime, DNS. DNS is the domain name system. We're going to explore it in our next lesson. DNS is there to do name resolution, principally, among lots of other things. Hey, DNS server, here's the name of a computer, what IP address goes with it. DNS can tell you. Sometimes we might have a scenario where I know somebody's IP address, but I don't know what name goes with it. So I do a reverse lookup against my DNS server and reverse the process. So in either of those cases, I want to be able to go hit a DNS server and expect to find answers. Those answers have to get there somewhere, in some way. Clients typically will register some of their information there. And there has been, ever since Windows 2000, an approach in which the client and the DHCP server share the process, share the responsibility for updating DNS with information about what's going on. And let me use a very sophisticated whiteboarding tool for that purpose to illustrate that point a little bit. So, we've got a DHCP server, we've got a DNS server, and over here off to the side I've got a client machine. What I want to be able to do is I want my client computer to be able to get his IP address information registered at the DNS server. DNS server wants to receive that information. It needs to get that information from somewhere. And there was a period of time where there was a manual process. You needed somebody to go visit the DNS server and configure the DNS server manually with that information. That is something that obviously we want to avoid, so our second best approach is to allow for automation. Our main mechanisms for getting that done, we're going to use a couple of techniques for that purpose. What we've historically done, ever since, again, Windows 2000, is that the client is responsible for calling the DNS server with what's referred to as its A record. The A record is what's sometimes referred to as the forward lookup record. This is the record that takes the name of the computer and makes an IP address out of it. So the A record is put into the computer, and it says something along the lines of computer 3 has an IP address of 172.18.38.55, for example. So that's an A record. This is the record that I will query in the DNS server in a forward lookup zone when I want to identify the IP address that goes with the name that I've got. Hey, DNS server, computer 3, do you know the IP address? DNS says, yeah, I got it right here, 172.18.38.55. That's the A record. The other side of the equation in most of our DNS work, we don't use it quite as often, but it is out there and something that deserves to be configured correctly, is what's referred to as a PTR record, a pointer record. Pointer records are reverse lookup records. They're a way to take a IP address and turn it around and make a name out of it. Well, where is that information going to come from? Could come from the client. The client could theoretically call the DNS server and supply that. What we've done historically is to let the DHCP server handle that. Because after all, the client's busy doing its A record lookup. The DHCP server has some spare time. And the client just got done calling the DHCP server and doing a discover offer request acknowledgement to be able to update the DHCP server, or to get from the DHCP server an IP address. So meanwhile, the client is calling the DNS server saying, hi, here's my name and my IP address. The DHCP server is calling the DNS server saying, hey, I just gave out this IP address to a client with this particular name. So this is just going to reverse the process we saw a moment ago, recording information in the DNS server that says there's an IP address called 172.18.38.55, and that belongs with a computer whose name is computer 3. Pretty straightforward. That's the regular order of business that we've seen for, again, quite some healthy long time. We've seen pointer records going from DHCP, and we've seen A records coming from clients. We're going to recommend going forward that we change that. And what we're going to do is we're essentially going to kill this basic idea that has all of our updating information for A records coming from client computers. We'll see that that's going to become important later again with IPAM, the Internet Protocol Address Management Utility, that's going to be interrogating DHCP servers, analyzing what's in their databases, and storing that in a central spot. It's going to unlock all sorts of neat behaviors. But we're going to kill the ability of A records to be updated from the client. And what we're going to do instead is we're going to have those A records come from the DHCP server instead. That's our basic strategy. Let's see how we do it. So we've been talking about a feature called Option 81 configuration. That would seem to suggest that we would go to the area in the DHCP console where we configure scope options and tweak it there. Seems logical. Let's jump to the GUI and see if that theory holds water. So here we are back on server 1. I want to be able to get at the Option 81 configuration, so the logical place to go would be, scope options, right? Right click, configure options. Oh, options have numbers. Good. Let's go find option number 81. There's 35, there's 67, and, no option 81. Well, where is it? It's hiding from us. Specifically, the place that it's hiding is if we go to the properties of our IP4 DHCP server node and pull up its properties. We can see that there is a tab related to DNS functionality here, and we can see the default behavior, which I'd been describing, in which DNS dynamic updates occur in such a way that the DHCP server dynamically updates DNS A and DNS PTR records only if the client says so. Ordinarily, the client says, don't worry about the A record, I got that, but if you would do me a favor and update the PTR record, that would be great. So the client requests that, the DHCP server complies and updates DNS. That's our main strategy and has been ever since Windows 2000. We're going to change that starting with Server 2012. We're going to recommend instead we configure option 81 this way. And as it turns out, the configuration settings that we've been making are driven by this GUI, but behind the scenes, the system is making changes to an option 81. We don't see it in the scope options part of the interface, but technically speaking, we are configuring option 81 for the DHCP server by configuring these settings. So, the new approach, DHCP server, responsible for both A record and PTR record updates. And again, that's going to be very, very handy for IPAM. If you want to be able to consult some more documentation along this line and see more of what's happening, what some of these other options mean, we've made the change that we really care about for our purposes now. But you might want to consider consulting Microsoft Knowledge Base article number 945397. You'll get a lengthy description of the different permutations of these options and what they mean behind the scenes. For our purposes, this will do for this discussion, and we're going to shift gears and look at name protection. So we finished configuring option 81. We know what that's all about. We've been able to hand off to DHCP responsibility for updating DNS data from the client computers. What happens next is we have to deal with something of a challenge created by that option 81 configuration. The challenge is, now that we've got DHCP doing all of the registration work, DNS doesn't know the original owner of the data that's being registered, and DHCP, once it's put data in DNS, by default kind of forgets what it's put in DNS. It did update that information on behalf of the client, but then it entirely forgets that it did so. The vulnerability is to something called name squatting, where I've got one computer that comes on the wire, it goes and calls DHCP, gets its information registered in DNS, everything is great, but then a second computer with the same computer name comes on the wire, and it calls DHCP, registers its information in DNS, and overwrites the data left behind by the prior client machine. All of a sudden, the computers that wanted to be able to call DNS with the name of the first computer getting its IP address instead get the IP address of the second computer. The first computer suddenly becomes unreachable because any attempt to retrieve its IP address from DNS fails. So let's take a look at how we resolve that interesting challenge. So here I am back on server 1, in which I can configure this name protection feature. That's going to be our solution to our problem here, something called name protection. We're going to deploy that either for IP version 4 or IP version 6 or both, depending upon which IP address protocols we're using in our network. Many organizations will use both in a transition period. Others might limit themselves to one or the other. On each IP protocol on which I'm using DHCP, I will want to turn on name protection on a Server 2012 environment. And let me do it on IP version 6 for starters. Let me right click here, pull up the properties of my IP version 6 side of my network. And I have the DNS tab. Again, this should look familiar. We saw something very similar a moment ago on the IP version 4 side. Down in the bottom right corner, I've got an option to turn on something called name protection. Name protection, again, is going to safeguard us against some of our challenges related to name squatting. Once name protection is turned on, whenever DHCP gets a request from a client says, please put my information in DNS, the DHCP server is going to put that name or IP address, or both, A record, PTR record, in DNS, but it's also going to record something called a DHCID, a dynamic host configuration identifier. And that's going to be used to be able to keep track of which computer that was. And that's a unique identifier based upon information about that particular computer, such that no other computer, even if it has the same computer name, will have that DHCID. So this is a way for the DHCP server to keep those different computers distinct from each other. So how do we turn it on? It's a fairly elementary process. Configure button. I can turn on the checkbox here to enable name protection. Having done that, we're ready to go. Very important notice here in the middle of the dialog I want to draw your attention to, though. It does point out that secure dynamic updates need to be enabled for this to work. Secure dynamic updates are a feature of DNS. Again, come on back for our installing Windows Server 2012 class. We'll talk in some detail about that procedure. But long story short, we're able to ensure that only members of the domain that contains the DHCP server, the DNS server, are able to get their information updated. We'll do that by storing the DNS data in Active Directory proper and using Active Directory security on that DNS zone so that only domain members are able to update it. So that's an important configuration. Having clicked OK here and here, we've turned that option on. Now, while we're here, I haven't done a lot with IP version 6 for you as of yet, so let me illustrate that. I'm going to right-click IP version 6 and create a new scope. Like IP version 4, that scope is going to need a name. We can see that here. Maybe I want to set up a IP version 6 scope for our Global Mantex Dallas office. With that done, we need a prefix. We need a range of IP addresses to work with. So IP version 6 provides 128 bits to describe an IP address, which is a stupefying number of IP addresses to work with. To be able to manage that well, we need to be able to get those IP addresses into the hands of somebody. Now, IP version 6 in general is designed for automatic assignment of IP addresses without even resorting to IP version 6. We'll come back to that in a different course. But for the time being, it's worth noting that we do have to identify, if we want to use IP version 6, a range of IP addresses to assign, much in the same way that we do with an IP version 4 range. So I will configure an IP version 6 prefix. Prefixes are the initial several bits in the IP address. We will identify what's essentially kind of like a subnet, if you want to think of it that way. I'm going to make an imaginary prefix 2001:ABCD:1. The colon is a compression of what would have been a long string of zeros in there. Preference is used in a case where I've got multiple IP version 6 DHCP servers. It allows the clients to choose which one is the preferable source for IP version 6 IP addresses. Following that, we've got room for exclusions. We saw that in our IP version 4 scope, same concept. Scope lease, same concept. Again, by default, we get to specify how long these addresses are valid to be used in the network before they must be handed over. IP6 addresses go through a range of what are referred to as lifetimes. We've got a preferred lifetime and a valid lifetime, after which those addresses are turned over for new ones. That being done, we've built a scope. I'm not going to bother to activate it just at the moment. But I do want to illustrate that building a scope in IP version 6 is really rather elementary. Before I move forward, let me just point out that I can also configure that name protection over here for IP version 4. If I wanted to confirm that if I go to the properties of my IP version 4 server, there is name protection functionality here as well, and it works the exact same way. So what we're seeing is in cases where name squatting is a concern, we can turn on name protection to be able to fix that problem. We're able to configure an environment where the DHCP server is smart enough to record extra information about the client in DNS to make sure that we are able to detect when a second client, maybe a non-Microsoft client, tries to squat on the name that a Microsoft client has already registered through DHCP in DNS. So the final topic I want to address as we look at DHCP functionality is DHCP failover logic. DHCP for a long period of time has been characterized by a very manual process for setting up failover logic. It's a very sensible thing to want to be able to set up multiple DHCP servers so that if one of them fails, that another DHCP server will be able to pick up the slack left behind by the failed server and keep IP addresses flowing in the network. We don't want a scenario where a client comes on the network, shouts, "Help, help, I need an IP address," does a discover, and finds no DHCP servers able to issue an IP address to that client. That's a problem. So what do we do to fix it? What we do is we configure multiple DHCP servers. The challenge historically is that DHCP servers that are configured to share a range of IP addresses were completely unaware of each other. There was no built-in knowledge in any one DHCP server of the existence of other DHCP servers, and consequently no way to be able to coordinate the efforts of multiple servers together. And that's something that changes in Server 2012. We can now configure DHCP servers in such a way where they can fail over, where one is aware of the other, they will keep their databases in synchronization, and in the case of the failure of one, we're able to pick up responsibility on another. Very interesting functionality, and I'm going to flip over to the server environment here to be able to illustrate what that looks like. So here we are on Server 2. Server 2 has been configured with the Global Mantex New York City office scope, which we can see has a range of some 25 or so addresses to it, small office, .50 through .75 in the 172.18.38 range of addresses. What I want to do is set up some redundancy. I've got just the one DHCP server. If that server fails, clients that need new addresses or need to renew their addresses are kind of out of luck. So now what do? Well, what we do is we do what's called a split scope. I have another server, server 1, and that's got the DHCP service on it as well. What I'd like to do is be able to split up the range of addresses so as to be able to divvy up maybe a fifth of them from one server and 4/5 from the other, or some other equitable arrangement so that my primary server handles most of the load, but in the case of a failure, we've got some addresses available from the other server. I could do all that manually, and that's what we would have done with a server 2003 server, for example. Server 2012 added, and 2012 continues, the idea of split scope, and I can access that right here. If I right-click the scope, advanced, split scope, I'm off to the races. It wants to know which server do I want to be able to hand off some of this server's scope to, and that's in this case going to be New York City server 1. It's going to take a moment to search for that server, and once it locates it, it's going to be able to give me the option to specify how much of the address space to move over to the other server. And there it is. So now I've got a range to be able to choose from. I've got a slider. We can see that at the moment the system is expecting to put 80% of the available addresses here at the host server, server 2, and shuffle some other 20% over to the other server, to server 1. The way it's going to do that is to create the same scope on both computers. You're thinking, well, wait a minute, Mike, we can't do that. We'll be giving out redundant IP addresses. Nope, we won't. And the reason why is down below here, you can see that we're setting a range of exclusions. We're excluding a certain portion of the address range from being handed out by each server. The host server, this server, server 2, is going to service 80% of that pool of IP addresses. It's doing so because it's excluding IP addresses 70 through 75 from the list of addresses that it's handing out. Meanwhile, the other server is going to exclude from possibility the handing out of IPs 50 through 69. So 70 through 75 are going to be at server 1. Everything up to 70 is going to be at server 2 where it started. Neat trick. I click Next. It wants to know if I want to set up a delay in milliseconds. Nifty feature. Remember our discussion of discover, offer, request, acquisition earlier. We identified that a client machine will query a DHCP server for an address. The server responds and says, sure, I've got an address. That happens separately for every DHCP server that hears that request. It might be some large number of DHCP servers. The client is going to respond to whichever one responds soonest. So, how do I make sure that both servers aren't responding at the same time? Well, what I do is I add an artificial delay to one of these servers, maybe to the one that I'm handing off part of the address space to. Even a small amount of time, 10 milliseconds, 20 milliseconds, 15, is probably plenty to be able to cause that server to respond just slow enough that a typical response gets handled by the main server and not the backup. It's a clever solution. Having done all that, we click Finish. It performs the processes that we called for. We can actually see that here if I look at server 1. If I refresh my address pool area, it now has an exclusion range that wasn't there a moment ago. The exclusion range covers addresses 172.18.38.70 through 172.18.38.75. That's the 6 addresses that we wanted to exclude. If I flip over to New York City Server 1, we can see the flip side of this same arrangement. Here's New York City Server 1, inside of which, if I refresh, I can see that it now has a copy of that scope. And inside of that scope, it has an address pool that covers .50 through .75. That's what it had over there on the other server. But note that it excludes IP addresses .50 through .69. The only ones this server will deploy is .70, 71, 72, 73, 74, and 75. 6 addresses out of 25. It's about 20%. It's exactly what we were looking for. I could have used the slider to have adjusted what quantity of addresses were being made available. This is a neat solution. This is a nice, simple, poor man's failover functionality, but there is a challenge there. Note that a computer that gets an IP address from one server but wants to renew it, if it tries to renew it against the other server, because the primary is down, the primary server doesn't really control that record. So now that we've looked at the option for split scope configuration, we've seen the potential benefits of it, it's worth reflecting on the fact that there are some limitations to it. If I do a split scope, if I take the IP addresses from one DHCP server and put a portion of it on a second server, that's a fine solution for new clients who need a new IP address. If they can't get it from one, they get it from the other. But what about those that have already got an IP address and want to renew? Well, renewal only works with the computer that owns that IP address. That server is down in the failover scenario. The redundant server doesn't have a copy of that IP address, almost certainly. So now what do? We could wait for that client to eventually time out using its IP address and get a new IP address from that other scope. That's a possibility, the other portion of the scope. But that's not optimal either. What would be neat would be to have a more self-aware failover solution. So we're actually going to shift gears into looking into exactly that. We're going to look at DHCP's other redundancy configuration, something called DHCP failover. DHCP failover clustering is our final solution that we're going to explore in this lesson. Provides a nifty technique for getting around one of the enduring problems of DHCP functionality, which is that DHCP servers were completely unaware of each other. Blissfully unaware of the existence of other DHCP servers like them, maybe just down the hall or elsewhere in the network, completely oblivious. No clue. So, what do we do about it? Well, one obvious solution might be to teach the DHCP servers about each other. It's a crazy idea, just might work. Microsoft had the same crazy idea. They said, let's get two DHCP servers to synchronize their databases with each other, passing DHCP update messages back and forth, so they can keep each other apprised of the changes in their databases, and that enables all sorts of nifty functionality. So here's server 1. Server 1 has got the New York City scope. That scope's got our 25 IP addresses in it. I've done a little bit of cleanup since the last example for those that are curious. That is what server 1 looks like. Let's take a look at server 2. Now here's something that you might not be aware of. You can, in your DHCP console, add the ability to go view some other server from that same point of view. I can, from here on server 1, go peek and see what's happening on that other authorized DHCP server whose name is server 2. It's going to think for a second. It's going to add server 2 to my console. And I'll be able to browse around and look and see what's happening inside of server 2 from right here, saving us the trouble of jumping back and forth between the two virtual machines. So there's server 2, inside of which, under IP version 4, if I refresh, no scopes. So no scope on server 2. There is a scope on server 1. I want to be able to make server 2 able to fill a redundant role for me. If server 1 crashes, I want server 2 to be able to do DHCP. If server 2 crashes, I want server 1 to be able to handle DHCP. How do we do that? In the past, that would have been really rather challenging. We could have done Windows failover clustering way back when. We would have done that under server 2012. That was our best option there. That has been largely replaced by the option we're about to configure that doesn't require failover clusters. It doesn't require shared storage between the two servers. All it requires is a little bit of configuration, and that's what we're going to show you here. I'm going to right-click my New York City scope and skip past the split scope area here under Advanced and go to this interesting option, Configure Failover. When we do, the failover GUI launches and prepares to ask which scopes on this server do I want to make available in whichever the other server is that this works with. This is designed for 2 servers and 2 servers only. And at the moment it's limited to only IP version 4, which is probably fine. Again, we're probably not going to be doing a lot of IP6 based deployment in DHCP, though it's possible. So, that being said, at the moment I've only got the one scope, the 172.18 range, so we'll deploy that. He wants to know where to. Well, unsurprisingly, we're going to send it over there to New York City Server 2. There's an option here to reuse existing failover relationships if there are any. I was monkeying with this earlier, so there is an earlier failover relationship that it could reconfigure for me. I want to show you the full extent of the wizard, so I'm going to deselect that. And that brings us to the main configuration settings screen for this feature, in which we start off with a relationship name. One DHCP server can technically be a member of multiple failover relationships with multiple other DHCP servers. Maybe server A and server B share a scope, server B and server C share some different scope. You could even imagine a hub and spoke environment in which in a corporate headquarters office, the local DHCP server in corporate headquarters is a redundant partner with dedicated branch office DHCP servers located in various spoke offices in a hub and spoke sort of a network topology. Something to think about. The relationship defines or identifies that particular set of configuration details that links this server with the one that we're building the relationship with. And again, one server can be a member of multiple partnerships of this sort. Beneath that, we've got a maximum client lead time. Let me double back for that for just a moment, because I want to draw your attention first to this important option. Load balanced versus hot standby configuration. We get our choice of one of two modes in which for DHCP failover to operate. Load balance is the first easy, obvious one to understand, in which we are going to split the available IP addresses in the range across two servers. And now, instead of doing 80-20, maybe we'll do 50-50. This is a very, very handy solution in a case where we've got two servers that are side by side, they're in the same LAN, they're servicing a particular network, and it's just straight redundancy. I want to make sure that if one falls down, the other one is still living. So about a 50-50 split is probably a fine choice. Load balancing will actually work in such a way where both servers continue to operate at the same time. If one happens to get a response to one client sooner than the other, great, so much the better. If the other guy gets there first, that's fine too. These two servers are splitting the load of managing this scope across the two servers, and they're working in tandem. They are going to synchronize their databases with each other so that both of them are aware of what the other one has done. It's a really rather nifty trick. To secure that communication, we can enable down here, if we choose to, message authentication. I can supply a secret. I'm not going to tell you what it is. It's really secret. And that, if I configure it correctly on both sides of the failover relationship, and that'll be done by this wizard, that will ensure secure communication of this data between those two servers. Now, I didn't tell you what the other mode was yet. The other mode is hot standby. Hot standby puts one server in the primary role and the other server in a backup role. We'll see that I can choose what the partner server is going to do. I'm here on server 1. I'm configuring a relationship with partner server, server 2. If I choose the option of standby, here I'm telling the partner that it will be the standby and I, server 1, will be the primary. Alternatively, I could say partner is going to be the active server. It's going to be the primary, and this server, server 1, is going to be the standby, the backup. So I get to configure that in either direction that I would like. When we configure hot standby, our goal is for one server to handle most of the work, but we want to be able to handle the scenario where a server goes offline and clients still want to be able to A, renew, B, register new addresses. We want to be able to handle that. To support that, the standby server will sit on a pool of 5% of the available IP addresses in that scope. It's not going to do anything with them. It's going to sit quietly and it's going to whistle to itself and wait for the time when the partner server goes down. When it does, that server is going to be able to begin handing out that range of addresses. The timing on that is governed by two parameters. One of them is this idea down here called a state switchover interval. The other is the MCLT, the maximum client lead time up above. State switchover interval deals with the fact that if the primary and the backup, the active and the standby servers, aren't able to communicate with each other, the standby can't be perfectly certain what happened to the active server. Is it still running and there's just a network interruption? Is that server in fact down? It's kind of hard to know. So the question is, how long will the standby server wait before it assumes that the other server is well and fully dead? By default, that's an hour. That's the state switchover interval. We could dial that down to some smaller number if we chose to. We can wait 10 minutes. If within 10 minutes of the time that we lose contact with the active server, it hasn't gotten back in touch with us, we're going to assume that it is down for the count, and we're going to take over full control of the whole scope. Until that time, of course, the standby does have access to its pool of 5% of the addresses that it can work with. Server goes incommunicado. We can't talk to the active server. The standby server is going to start doing work with its pool of 5%, waiting for the opportunity to take over the whole range. That'll happen after the state switchover, an additional delay time called the maximum client lead time, MCLT. So that's just an additional safeguard buffer to make sure that we're not inadvertently stepping on the toes of a active server that is temporarily out of commission. So we get our choice of mode, we get our choice of configuration details once we've chosen the mode. We click Next. It prepares to make that change on server 2, and that all happens automatically. It happens right from here. If I go look at things from server 2's side, do you see the failover relationship? Trick question. No, you don't. It's hiding. Common sense would say we'd see some sort of a failover configuration node here underneath IP version 4. It's not there. The place to find it is if we right-click, pull up the properties of the server. There is the failover tab. And I can see here, the one that I just created configures a hot standby configuration. We can see the details here. And note something interesting. We have the option, if we're in the communication down state, to force this server to go into its partner down state, where we're going to tell it, yeah, trust us, that other server, it's not coming back for a while. You go be the primary. And this server steps up and takes on the role of being the active server until eventually the active server comes back online and everything goes back to normal. But it is possible to force a server into the partner down state. But I can see all of my failover relationship parameters here. I can tweak them from this point. It is also possible, of course, to throw all those options away. The delete button will discard those options. I can right-click a server and deconfigure failover from the server on which I launched it. So there's the deconfigure option at my disposal. Wonderful functionality. This is failover capability that used to require a Windows failover cluster. Multiple servers using shared SAN type storage, things of that sort, using the Windows failover cluster functionality. That is no longer necessary. That functionality is native to DHCP. I don't need to go out and buy special SAN equipment or things of that sort to make it work. It's native to the feature. It's a wonderful benefit. Thanks for being a part of this lesson. I look forward to delivering the next one to you.